Hello Year 11, and instead of your 5 a day, here's a different starter for you. Okay, and let's go through the answers. So, we're going to be using our SOHCAHTOA trigonometry ratios. So, we're going to start in this triangle here, and we want to find this opposite side. So, I've got the adjacent side, I've got the angle 42, so I'm going to use tan. So the opposite is tan 42 times 8, which is 7.2. I've rounded that to 2 decimal places to put it there, but you should have kept the full decimal on your calculator. So now I know this length, so I'm going to subtract that from the length of the hypotenuse of this bottom triangle to find the side length of the square. So here, this is my angle, 24. I want the hypotenuse, I've got the adjacent, so I'm going to be using cos. Substitute the values in that I know. So I know this whole length is 13.14, and I subtract the 7.2 from it to get the side length of the square, which is 5.93. It's a square, so I know that this is also 5.93. So I've got this opposite side and I've got this hypotenuse, so I'm going to use sine in the third triangle. And then inverse sine of 9.93 over 13 gives me 49.82 degrees to 2 decimal places. So today we're going to be looking at problems in 3 dimensions, how we can use Pythagoras theorem and trigonometry in 3D. In fact, the questions that you do won't be too dissimilar from the one that you just did, because the main thing to remember, so we've used trigonometry a lot. Today we're going to look at it in 3D. The main thing to remember is think about all the separate parts of the questions in 2 dimensions when we're answering questions in 3 dimensions. And making quick sketches of the triangles that you're working on as we go through will help to visualize what you're doing. So let's have a look at a few examples. Here's a cuboid. It's a 7 by 4 by 6 cuboid. We're asked to find the length BH here. Now what we can do is we can have a look at the length BD. We can find the length BD to begin with. We have a right-angled triangle on the base of our cuboid here. So here's my triangle. It's 4 and 7. And I'm going to be using Pythagoras theorem, so I'm going to state that that's a squared plus b squared equals c squared. Remember, c is my hypotenuse, the a and the b are the legs. It doesn't matter which way round they go. Substitute in the values I know, evaluate the squares and add them together, and then square root. So I know that c is the square root of 65, and I'm going to leave it as the square root of 65 for now. So let's label that on the diagram. That's some pretty rubbish writing, sorry. Okay, now hopefully you can see that I've got another right-angled triangle here. Remember, I'm looking for BH. I now have BD. I also have DH because it's 6. So I'm going to draw myself this triangle. It's a good idea, especially in this kind of situation where my vertices are labelled, to label them on the diagrams that you draw as well, so you don't forget what part of your question shape you're working on. So here we're working on the triangle DHB. So again, I'm going to use Pythagoras to find BH. BH is my hypotenuse. So I substitute the other 2 lengths in for A and B, evaluate the squares and add them together, and then square root. So I know that BH is square root of 101. Now, there is a quicker way. What you can do is just square the 3 dimensions, so 6 squared plus 7 squared plus 4 squared, and square root it. Relatively straightforward to show how that works. You can do it with using this kind of idea. So I'll leave you to have a go at that if you want to. But for a cuboid with dimensions a by b by c, the length of the diagonal is the square root of a squared plus b squared plus c squared, and you can jump straight to that. So let's have a look at using trigonometry in 3D. Here we want to calculate the angle between BH and the base of the cuboid. So here's BH, which we found before as the square root of 101. We also found BD before, that was the square root of 65. It doesn't matter which one you use, I'm going to use the square root of 65. Remember that this is 6, this is the square root of 101. So I'm going to use this triangle here. I've got opposite and adjacent, so I'm going to say tan theta equals 6 over the square root of 65. So theta is the inverse tan of 6 over root 65. And I get theta is 36.7 to 1 decimal place. Another example. So the Great Pyramid of Giza is a square-based pyramid of side length 230 and is 139 meters high. If you were to stand in one corner, here for example, and walk up the pyramid to the top, along the edge here, what angle would you be walking up at and how far would you have to walk? So here's a diagram that we're going to be working off of. First, we need to find the length of the diagonal of the base down here. Both of the sides are 230. Here's my triangle, 230, both of the legs. So I'm going to work out C, substitute in the 230s, square and add, and square root. Again, it's best to keep this as an exact value on your calculator. Now I've got that value, I need just half of it to make this right-angled triangle here. So I divide it by 2. And this is the triangle I'm going to be working with now. So I'm asked to find the angle. I've got opposite and adjacent, so I'm using tan. Substitute the values in. And inverse tan. I get 40.5 to 1 decimal place. To find the distance, I can use trigonometry or Pythagoras. Let's go for Pythagoras. Substitute the values in, evaluate and add, and square root. Okay, so that should be enough for you to work through questions 1 to 11 from exercise 13G now. Remember, at each step, draw yourself a right-angled triangle, fill in the information that you need, and work it out. Be really clear as well with labelling vertices so you know which triangle you're working on. So let me know if you have any questions and make sure you mark your work. Thank you very much.